Welcome back to After Hours Engineering. In the previous episode, we began construction of a functional control matrix that included several decodings for real instructions, for example, the load immediate. In this episode, we finish coding and simulating the rest of the instructions. However, before we launch into the new instructions, we need to backtrack a bit and look at some code that I overlooked when we were adding these new instructions, namely the registers holding the control signals. Once we're done coding and simulating, we'll write a few complex programs that are better illustrated and synthesized on an FPGA. Let's get to it. Here we are in the control matrix. Let's review what's needed to add a new instruction by using the PC load signal as an example. You can see up here, outside of the always block down here, I have the PC load register defined. Do a Control F, and we scroll down, you'll see that I also set up an initial default value for it just outside of the case statement, and this is the area where we're looking at minimizing latches being formed. So if we come down here, we'll see that I'm now using that value, and if we scroll all the way to the bottom, you'll see the final step, which is to take that signal and route it to the output here. So let's begin by starting our new instruction, the shift left logical. And as usual, we're going to start here on the decode statement. So we'll scroll down here to the shift left, and you can see that I am setting the ALU operation to the operation specified in the instruction itself. We're also setting the next state to ALU execute, as the logical operation needs one extra cycle to perform its work. We'll scroll down here and we'll notice that there is a new section here for the ALU operation, and it checks to see if it's equal to 1111. The reason is because if there is no ALU operation, this is the value that it will be. However, if it is an ALU operation, it will not equal that value, and we'll set the ALU load and the flag loads to active states. We'll come down here to the ALU active, and you can see that we're going right back to the fetch state once the cycle has completed, and we reselect our data source and our write register enabled to write the results. This is the write back in a lot of other processors. Now let's look at the program for the shift left operator. In this case, I've cooked up a very simple program that will take the least significant bit and shift it left 5 places, putting the bit right here. So R1 will contain the bit, R2 is how many places we're shifting by, and then this is the shift left operator itself, and this is the instruction code for it. We're using Verilog's built-in shift operator, in this case the logical shift operator, and then finally we output the result and halt. So now let's take a look at the simulation. Before we get started, let's review the signals over here to the left. It's been a while since the previous episode, so let's take a look. We have our halt signal, which is staying low until we hit the halt instruction. That's what we expect. We know that when the CPU is in its fully functional state, the ready flag has gone high, and that's what we're seeing here until we hit the halt. We can see that our state and next state vector states are all proceeding in the fashion that we expect: decode, fetch, and with an occasional extra execute state in between. That's good. We see that our instruction register is constantly being loaded with each one of the instructions that we have here. That's great. And we know that we're incrementing the PC counter with every instruction that we see, with an extra cycle here with the ALU execute. Excellent. We know that we are also writing to the register as we load them. The 2 load instructions cause the register write to go low, and we also notice we have a write here as well, and we'll talk about this in a minute when we get to the shift left. We have our register file here, and it is operating as expected. We'll talk about the registry settings here. We definitely have some ALU activity this time. The shift left is embedded in the ALU. Some processors don't do that. They may put it in a separate unit. And then we have our extenders, which are not being used here, and our outputs, which you've seen. So let's take a look at the program itself and go through and make sure that it is executing the program as we expect. We know that in our program we had the load and then an output, another load for the number of times we're going to shift, then output it, and then our new instruction. Here's the shift left. And we can tell things are going on a little bit different. For example, if we come down here to the registry file section, we can see that the instruction itself defined and used register 1 as destination, and that's what we see here. We also see that the two sources was register 1 and register 2. Excellent. That's what we also see. We can also see that the ALU operation has been recognized as the shift left. Excellent. And the flag statuses themselves have gone active. Excellent. That's what we expect to see as well. Now we know that the shift left is going to add in an extra cycle, the ALU execute cycle. And if we come down here to the data source, we can see that the data source has changed to something new that we haven't seen before, and that's ALU results. So after the shift operation, we place the value of what was shifted into the destination register, which is register 1. And if we look on source 1, we can see that the 0020, that's the shifted left results. We're also going to see, if we come down here to the bottom, the output, because the last instruction outputs register 1. And sure enough, it's 0020. So this program is operating exactly as we expect. Up next is the shift right operator, and we won't cover it too heavily as it is almost identical to the shift left, except of course that it's shifting everything to the right. But you can see that we've added an extra state for ALU execute. We've set the ALU operation based on the bits in the instruction itself. If we scroll down here, we have the same set of checks for setting the ALU flag and the flag register itself. And of course we have that basic execute, and we have the ALU execute, and as before, as soon as the ALU execute is finished, it moves immediately to the fetch state. We also set our data source to the output of the ALU, and we turn on writing of the register file. Next is the add instruction. Again, starting up here at the decode, we have immediately the add instruction. In this case, we set the ALU execute as before and the operation for it. If we scroll down here to the bottom, we'll see that it is an ALU operation, so these two flags will go low, and we're exercising the ALU in this state right here. And again, when we move from execute to fetch, that's when we store the results in the register file itself based on the selected source from the diagram. Now we'll take a look at the program for the add, and again it's pretty simple. We just add 2 plus 5, and that should be 7. We load register 1 with one of the operands, register 2 with the other operand, and then we add them, placing the results in 3, and then write it to the output, and then halt. Now we'll take a look at the output of the simulation for the add instruction. Again, we'll double check that our program is running as expected. We have the load of the first operand, we load the second operand, we output it, and then we have our new instruction, the add. And as you can see here, the destination is set to register 3, and the two operands, register 1 and register 2, have been selected. And as expected on the ALU execute, we have that extra cycle that allows us to read the ALU results and write it to the destination, which is register 3. And then we output register 3, and sure enough, it is the number 7. It's exactly what we expected. And if we look at the flags out, we'll notice that none of them are set. And that's because we had no 0 results, negatives, or overflows. Any of those values were not triggered, so that's as we expect as well. So the add instruction is setting the flags accordingly. Next is the subtract instruction, and it is nearly identical to the add instruction. So scrolling down here, we can see it. The difference between it and add is the subtract can double as a compare instruction, and compares, you typically don't store the results, you're just interested in the flags. So in the instruction itself, you have this ignore destination bit. If it's a 0, then that means that we need the extra cycle to store the results. In this case, it's an actual subtract instruction. If it's a 1, then this is a compare instruction, and we don't care about where the results goes. It goes off into deep space effectively. And again, the usual, we have the ALU operation being set. We come down here, we can see that it is an ALU operation. It'll set the 2 flags. And depending on whether that ignore destination flag has been set, we may or may not execute this state here. And we'll see this later on in some other programs when we use the compare instruction. And finally, we make it to our last instruction, the branch on not equal. So let's take a look at that. If we start from the top here, we see we have our decode. We scroll down here to the branch on not equal. In this case, we set our branch source to the sign extended version because the branch allows us to branch both forward and backwards in memory. Remember that branching is the very act of loading the program counter with an address that we're going to actually fetch the next instruction from. And of course, we set the PC source to the actual branch source, which in this case is the output of the ALU. And then finally, we reset the flags because we really don't need them anymore. We've just made the check of the flags. We don't need it. And then we need 1 extra cycle for the branch instruction itself to finish executing. If we scroll down here to the branch basic execute, you'll see that it doesn't do anything but give us that extra cycle. You could set more variables here if you want, more signals, but we don't. Immediately switching to the fetch cycle. Here is the assembly program for the branch not equal. And in this case, we're checking to see if the Z flag was not set. So we load 2 numbers, the number 2 and 5, and we add them together, and that gives us 7. That means that this branch should take place because the 0 flag was not set. So the output of the program should be a 4 and not 7 as it would be on line 5. Here's the GTK wave output for the branch on not equal instruction. The first thing we're going to do is look to see if the program actually flowed in the manner that we expect. And what we were expecting is that the load of register 1 happened, the load of register 2 happened, the add happened, and then we output that value, then the branch on not equal happens. At this point, there's 2 directions it could head off into. It could go to the NoOp instruction, or it could branch down to the load immediate instruction. We want it to branch, and sure enough, it has. Here's the load immediate, then the output of the results, and then the halt instruction. The final value on the output should be the number 4, and it is. So let's take a look at the branch on not equal. This instruction is reacting to the add instruction that happened previously. And as you can see from the add, there was no Z flag that was set because 2 plus 5 equals 7, which is not 0, so the Z flag is not set. The branch on not equal is reacting to that. You'll also know that the flag reset has gone low as well because we no longer need those flags anymore. So it looks like the program is doing exactly what we expect. Okay, with all the instructions complete and simulated, we're ready to synthesize. But before we jump in, we need to do a few things first. One, we need to actually build the CPU, which means we contain all the components that we built up to this point. Next, we build the top module that contains that CPU. Then we'll review a new memory configuration or ROM configuration. We'll look at the make file to support our new target and the pin constraint file to go along with it. In addition, we're going to synthesize, as mentioned, a brand new target, the Black Ice MX. And that's what we have here. I'll show it to you. There's the Black Ice MX. It's from Volcanology. On the top is the carrier board and the bottom board with it, or the core. The top you're looking at is the core, and beneath it is the carrier board. And down bottom is all of my LEDs that I've put onto a prototype board. Okay, let's take a look at the CPU module first. And it's like any other module. It has some parameters, inputs, and outputs. These extra outputs are not really part of the CPU itself. They're for debugging. The real outputs are just these 2 control signals right here. And we have sizes for different muxes. We have all of our internal wires that will connect all those components together. We've seen this before in some of our other synthesis modules. And we have all of our internal signal tracking registers and wires. We have some defines that help us break down the instruction register. We've seen that before. Some defines for the ALU, the instruction register, the address upper and lower, a bunch of sign extension or extenders, or expanders as someone might call, and branch address mux, the reset vector, and then this is our first component that we're containing within our CPU, and it's the most important one, of course, and it's the last one we did. You recognize it. It's the control matrix, or as a sequence control. We have our program counter, the raw memory, register file, ALU, all of our muxes that put everything together, the mux PC, the branch, the mux data, the mux output. We have that one small mux down there by the register file for the destination. And then we have all of our registers. The most important, the instruction register, the stack, the ALU results, the ALU flags, and then our debug register, the output. And then finally at the bottom, we route all of our internal signals to the output. This is pretty much like all of our modules, and it's no different. So let's move on to the top module next, and I've given the file the very clever name of A09. Like all of our modules, we have inputs and outputs. This clock is the onboard clock of the device itself, which you can see in the display over here to the right. And we have two more wires that come into the device, which you can see over here to these two wires right there. And then we have two extra output wires and then all of the control signals that go to my LEDs down below. These two control signals will hold the blinking green LED that you see up top, and this one will hold the instruction register load flag, and it's yellow. So we'll see it turn yellow as we're moving through the program. We have some defines as usual for data widths and address widths. We have some registers to hold our information. You've seen this circuitry before. This is the clock that's driving that blinking green light at the top. And here it is. Here is the A09 CPU. And as before, we have a clock input, we have the reset input, and we have two outputs. In addition, we have some extra outputs for visually driving our LEDs. Normally you wouldn't have these on your actual CPU. And this diagram here, these comments right here, define the pinout of the target device, or our Black Ice MX. And I'll show you the pin constraint file that goes along with these numbers. And then finally, we route all of the signals to the LEDs themselves. This is the white section, and then the four blue lights, the two yellows, the red, and the green. And then the blinking green light that you see up top. And then this is for the output load. I was saying instruction register, but it's actually the load signal for the output, which we'll see go low just prior to loading the output register. This is the pin constraint for the Black Ice MX. It's very specific to the target. This first pin is actually available only to the crystal, and it is the 25 megahertz crystal on the device itself. It's right over here, just above the static RAM. It's this small little crystal right there. The next pin, 52, is also only available directly off of the device, and in this case it's going to be our blinking light. That's the green blinking light you see at the top. Then we have the output load signal. This one is available on the PMOD. The rest of these are also available in the PMOD. They have to be because that's what we're using both as our input, the two inputs, the clock and the reset from the microcontroller, and then all of the outputs for the LEDs down below, the white ones and then the colored LEDs. This is our new memory module. It's a ROM module. It only has the ability to read. It has no write features. I've done this so we can take a look at what a ROM actually is. But I need to cover something first. It's very important to this. You'll notice that I have this mem content defined here, whereas in the simulations that we were doing, I was passing that in on the console. And the issue seems to be with Yosys. It doesn't like the double tick marks that we were using to pull in information off of the console. So I've had to move back to embedded define statements in order to pick this up. If I don't do this, what happens is that the toolchain fails to actually generate RAM, and as a consequence, it will fail to generate all the other components in our CPU, and what we end up with is just the top module. We don't actually get anything else. And you'll see this in a minute when we look at the logs. You'll see that no RAM was generated, and there was only a very small set of logical elements generated. So let's take a look at what it takes to make a ROM file. And it's not much. It's just an always statement. In this case, I've chosen the negative edge to read on. And we're just simply, on every negative edge, we're writing the memory contents out to data out. And that's it. So let's look at what happens if you don't actually define any contents in memory. And that's this section right here. If I were to go to the make file and remove this one line, no ROM contents will be embedded into the FPGA. And so the toolchain will say, well, no memory, no need for any of these other components, and the routing tool will have nothing to do, and so it will only route what's in the top module. Finally, we'll look at the make file. This particular make file is specific to the Black Ice MX. That's why it's sitting in the Black Ice MX folder. Like anything, we need to define our top file, which is the A09. Any of the submodules that are part of the project itself, of course our control matrix and all of the components, register files, program counters, they all need to be included for Yosys to compile. If you leave any one out, you'll get the ubiquitous error of XYZ is not part of the design, which means you've almost certainly left one of these out. The only other reason that this typically comes out is if you have non-compliant ASCII characters in there. That can also throw it off. Let's scroll down here and take a look. We have the target port, which is TTY-ACM0. Our pin constraint file. Here on the build is the typical Yosys command running this synthesis ICE40. The Black Ice MX has an ICE40 on it. What it has is the bigger package, the one with 144 pins on it. So the package is different, as well as this parameter right here. This is the HX8K. The upload is slightly different as well. It's two commands to actually output the bin file to the target. You have to first set the target to raw, and then you concatenate the bin file right out to the target itself. And that's it. Let's return to the ROM file and look to see what happens when you don't actually fill the ROM with any contents in and of itself. In order to do that, I'm going to specifically leave out the use ROM. I'm going to do this on purpose. So we'll remove the flag for that and leave it out. And now we will go and run the synthesis and the next PNR tools, or place and route tools, to see what happens when we don't have anything in the ROM itself. So let me bring up the terminal here, and I'm going to type in the build command for Yosys right there, and now it's run Yosys. So let me come over here and bring up the logs so we can see the logs. Take that down and reload the Yosys one. We're going to come down here to the flatten section, and you'll notice this isn't right. It's literally saying it's deleting all of our components out of here. And the reason why it's doing this is because it failed to actually detect any RAM. And with no RAM, you don't have anything else in your CPU. So if we come down to the last section of the BRAM inference section, we can see that it failed on every attempt to try to get some sort of inference for RAM. That's our first clue that something isn't right. So let's look at the next clue. So we'll come to the terminal here and bring that up. And we're going to run the make route command this time. This will run next PNR. And you can see that it returned really fast. You'll see that if it does work, it does hesitate calculating things out. So let's take a look at the output of the logs. So we'll bring the logs back up, come over here to next PNR, reload, and we'll scroll down to the section that tells us what was utilized on the device. And sure enough, this is 0. That's not good. That means that it failed to actually synthesize any kind of RAM, or at least the BRAM that we wanted. And also, notice that this number is really, really low. Our CPU, even as simple as it is, takes about 500 or 600 LUTs to actually form logic elements. and we're only at 67. This number is low because all it synthesized, or ended up synthesizing, was the top module. It didn't synthesize anything. It completely deleted all the components and then the CPU itself. So that's not right either. So with nothing in ROM, the toolchain will not synthesize anything for memory, which causes nothing to be synthesized for the CPU itself. So let's go back to the makefile and add in this feature, which I've already done. This will actually fill the ROM back up. So we've saved that out. Now we'll bring up the terminal and I'll type in make build like that. And you'll notice that it takes a little bit longer to run that time. Now we'll take a look at our log files. We'll turn that on. We'll come over here to YoLog and reload, and we'll head on down to the BRAM section. And you can see this time that it is still failing on some of the rules. But if we keep scrolling down through the failures, eventually it will arrive to a correct solution. In this case, this is the line that we're looking for, the creating line. And you can see that it has created a BRAM of mode 0. Excellent. That's exactly what we're looking for. So now we'll run the route tool to see how well it did on the device utilization. That's our other clue. So we'll bring the terminal back up here like that. And we'll take make route like that. And there it goes. It just ran the route tool. So we'll turn that back off. We'll go back to our logs and we'll reload that. We'll scroll down to our utilization, and yay, we actually have block RAM defined. You'll also notice that the logic count has gone back up into the 500s, which means it didn't delete all of the CPU and components. It actually synthesized this time. Excellent. That's what we were expecting for our CPU to be correctly synthesized. We're now ready to upload it to the actual device itself. Congratulations, you've made it this far. At last, after all this time, the rubber is hitting the road. It's time to synthesize our CPU onto the FPGA. As you recall, we need to embed our program into the ROM, and for that, we'll start with the NoOp program. You can see here, I brought up the ROM memory, and in it, we set our mem contents to what program we want to execute. In this case, we're going to execute the NoOp halt instruction. If we go back to the README file, which contains all the assembly, you can see that it's really simple. It does literally nothing, but it will allow us to see the lights blink on the display below. So we've got our NoOp in there. Now I'll bring up the terminal and I will type make all. Now in this case, because this is the Black Ice MX, I don't have to hit any buttons. As soon as I do a make all, it will build, route, and then upload it onto the Black Ice. And you'll see the lights blink up top as it's happening. So look at the top when this goes off. So there it goes, building it, and now it's uploaded. Now I'll bring up the controller program that I use, and that's these wires over here to the left of the Black Ice. And these two are the clock and the reset. So I'll hit the X key, and you'll see that the instruction register, the lights are changing. And I'm just going to march through this real quick just so we can see it changing. Now let's take a look at the LEDs that are down here at the bottom on the prototype board. You should remember that that is the same pattern that I had on the tiny FPGA, but I was using a breadboard in order to hold the LEDs. In this case, I've wired them up to the two PMODs that are on this edge of the connector. And as before, we have blues, yellow, red is the halt, and the green is the ready. And then all of this would be any data that we have going on in our simulation. Okay, now that the CPU is uploaded, it's most likely in some random state. However, because our initial states are both defined with a value of 0, it happens to fall into the correct state. And here is the initial state for reset and the initial vector state, and they're both defined as 0. Excellent. Now let's look at all the LED states and make sure they are in an expected state at the start of the reset sequence. As a quick note, the LEDs at the bottom are all positive logic, and I've switched the top LEDs to positive logic as well. And what that means is that if we see a 1, the LED is on. If we see a 0, the LED is off. So if we scroll up top here, we can see that the ready signal is set to a 1, yet the LED is off. And again, if we scroll down here to the bottom, right here we can see that as our processor comes up, it's in the reset state, so ready is actually turned off, and we're in vector state 1, so we'll also see that the PC load is off as well. So if we scroll back up top here, we can see that the PC load defaults to 1, but because we're in vector state 1, it's off. That's correct. Excellent. The halt is also off, as we expect. The PC increment is on. That's the red light. And the PC load is blue. And again, that's off, as we saw below. The instruction register load is on. The output load is also on. And they're on, indicating they're not active. If they were off, they're in their active state. The signals themselves are actually active low. We scroll down here a little bit, we can see that the register write enable is also on, which is what we expect. So all the signals are in their state as they should be on a reset. And finally, the instruction register, which is all the blue lights, they are all off because no instruction has been loaded yet, which is what we expect. We also have the halt and the ready are in their correct states. And then over to the right, all the white LEDs are off because we haven't loaded any data into the output register. So that's great. The reset sequence is starting off correct. At this point, it's time to bring up the monitor controller so that we can begin sending clock signals to our CPU. This will allow us to step through our state machine on a per clock basis. So come over here to the terminal, and I'll hit return, and it's starting up the monitor. And as you can see, it takes 3 keys, or it'll emit 2 signals, and 1 will control the clock. The X key sends out 1 clock to the CPU. The Z key sends out the reset signal, and as you can see here, the C key will toggle on and off whether the clock is free running or halted, and it defaults to halted. So let's take a look at our reset state. We can see that the ready flag is low, so the signal, or the LED in this case, is off, and that's correct. Now, as a reminder, this is the reset state, so it's the CPU hasn't actually entered into its complete running state. So both the halt and the ready will be low. Again, we're also starting off in vector 1 state underneath the main state itself, the vector state. And we can see that the PC source will be set to 0, 1, 0, which is selecting the reset vector constant. And we notice that the PC load signal is also low. The LED is off. Excellent. Now I'll come over here and we'll run the clock once. And you'll see that the instruction register load signal has gone low. And that's what we expect. Excellent. Now I'll do the clock one more time. And you can see that it's gone back on. Again, it went back on because its default value is to be on. And there it is. It's on. So if I come down here, we also set in vector state 3, the PC source is now switched to 100. We saw this when we were looking at the simulation. So nothing has changed here. We also notice that the PC load flag has remained low, and that's what we expect. And finally, the internal signal for reset is set, and that's what we expect. Excellent. As a quick review of the reset sequence, the goal is to fetch from the bottom of memory a starting address for our program. And that starting address comes from the lower 8 bytes of the instruction at that location at the bottom of memory. It's technically not an instruction, as it's really just an address in the lower 8 bytes. And that is routed through the 0 extend low up to the PC. And that is what we see going on right here. And we saw the PC load go low, and we would have seen, if I'd have hooked it up, the 1001 on the MUX selecting the 0 extend channel. Now we're at the end of the reset sequence, which is vector 3. We're ready, and we will transition to the ready state once I execute the next clock cycle. And what we should see is the ready flag, or the ready signal, the green LED at the bottom, turn on. Let's go ahead and do that. We'll hit the X key, and sure enough, the green LED has turned on. The question is why is that? You don't see in the ready state anywhere where I'm activating that particular signal. The reason is that while we are in the reset state, I'll collapse these so you can see this better. While we're in the upper reset state, the ready flag is constantly being held low. And this particular state right here, let's collapse that, is constantly keeping us in the vector state. As soon as we transition to this one, we'll come down to this case statement, which exits us out of the reset sequence. And in this case, if we scroll all the way up to the top, we'll see that the ready flag, or the ready signal, has been set high. And that's exactly what we expect. If I hit the clock again, we will then transition to the fetch sequence and begin fetching the very first instruction of memory. Let's send another clock signal to the CPU so we can transition from the ready state that we're in to the fetch state. As you can see here on this line, the next state will be the fetch state, and it is set there. But nothing has happened because I haven't sent a clock to the CPU. And what that will do is it will trigger our synchronous circuit. As soon as I toggle that clock, it will come down here and execute this statement. We know that we've set the complete flag set to a true, so we will take the next state, which is the fetch state, and transfer it into the currently running state. So if we scroll back up here to the top, collapse the decode, I'm going to go ahead and give it a clock. So I'll come over here to the terminal and hit the X key. We should see the instruction register load signal go low and the PC increment go low. That's the red flag up at the top by the HDMI connector. So let me go ahead and add that, and sure enough, the instruction register went low and the PC increment went low. And that's exactly what we expect during the fetch cycle, because we are trying to fetch the instruction from memory into the instruction register. And also we want to take advantage of the clock cycle to increment our PC. We are now in the fetch state, ready to transition to the decode state. And as you saw, that the instruction register and the PCs are in their current state that they should be in. Now we're ready to send another clock, and we should transition into the decode state. And in that, we'll fetch the first instruction, which is the NoOp instruction. So let's go ahead and give another clock. And there you go. The instruction 0001 has been loaded into the instruction register. That's exactly what we wanted. And if I was to show the program counter, we'd see that it was incremented, which we saw in the simulation. Excellent. And as a default state, because NoOp doesn't do anything, we automatically will go back to the fetch state right back up here. So on the next clock cycle, we should see the instruction register signal go low again, and as you can see, it's currently gone high, because if I scroll all the way up to the top, you can see that its default state is a 1. That's exactly what we're expecting. So far, the state machine is following our code exactly. So let's go ahead and clock it one more time, and we should see the instruction load signal go low. So I'll clock it, and sure enough, it went low, and the program incrementer went low. And that's what we're expecting. So we'll give it another clock, and this time it should load the next instruction, which we know for our very simple program, we just executed this one, should be the halt instruction. So we should see this binary pattern appear on those lower 4 blue LEDs. So let's go ahead and give it another clock signal, and sure enough, 1011. Excellent, we've just loaded and executed our next instruction. So if I come all the way down here to the bottom, we can see that for the halt instruction that we covered in a previous episode, the next state is, instead of being a fetch, we're overriding the default behavior and setting it to the halt state. So for that, we'll need to scroll up and find the halt state. There it is. So this is where it's going to go. And what we expect is the halt flag, or the red LED next to the green one, to go high, and the ready will go low. So let's go ahead and give it another clock and see what happens. And sure enough, that's exactly what happened. We're now in the halt state, and we'll never leave it because the next state is always the halt state. So if I come down here and just keep clicking the clock, nothing is happening. It's stuck. The whole processor is halted now. The halt is red, has gone high, and the ready is stuck in a low. This is exactly what we were hoping for with our program. So far everything is working according to the program. Excellent. This is awesome. We've run our very first program on our Softcore processor. The A09 lives. Sweet. Say, how about we take the next step and load a register? For that, we'll need to update our ROM to contain the new program. So here we are in the README file with all of our assembly, and this is the next program we're going to execute. It'll be a NoOp. We'll load one of the registers, in this case register 1, with a number, A05, and then we'll halt. So we'll grab this name right here. We'll come over to our memory. We'll paste it right there. And then we'll need to run the make all program and upload it into the FPGA. So I'll go ahead and do a make all right here. And there it is, loading it in. And there we go. Our new program is now loaded into the FPGA. So come back over here to the monitor, and it defaults to the reset state, but I'll just reset it manually. Doesn't do anything. And now we're going to switch over to the README, and let's just follow along with the program. We won't worry about the signals right now. Let's just have a little bit of fun and follow along. So I'll give it a clock to start the reset sequence. It's now going through the reset sequence, fetching, and now it's getting ready to fetch the first instruction. Yay, there it is, 001. Excellent. I'll go ahead and give it some more clocks to get the next instruction. There it is, 1001. Excellent. It's going to load register 1 with a A05. Now I'll give it another clock, and it should hit the halt. 2 clocks, and there it is, 1011. Excellent. The program has reached the last instruction, and of course I'll give it some more clocks, and we have halted. Excellent. We've just executed our second program. Now we'll back up and monitor the state machine once again. So I'll come over here to the window and reset our processor. You'll notice that all the flags change back to their default states. We'll bring up our control matrix, and we'll be right here at the fetch state, at the ready. We'll walk through the reset one more time. Bring it open, all these here, pop these open. Okay, so we're at the reset. We know that the 2 yellow signals will be high. So we'll give it a clock, and there it goes. It went low. So the instruction register has gone low. We've entered this state. We started out up here because we always start in the reset vector 1, and the first clock moves us to vector 2. That's what we expect, and the instruction load went low. Again, just as a reminder, we're not actually loading an instruction, we're in the reset sequence, and so it's actually fetching an address, and it'll show up in the lower 8 bits of the instruction register. So let's give it one more clock, and there the instruction load has gone high, so we're now in vector state 3. We'll give it one more clock, and the PC load indicator has gone as well. Excellent. So we're in vector 3, and we're actually in the ready state. We've come through vector 3 and gone into the ready state, and so the ready flag has gone high, and that's what you see here. So I was one step behind. So we're going to give it one more clock, and this is going to begin the fetch sequence. So I'll give it another clock. There, the instruction load went low, and the next clock, it's loaded. Remember, it's in between states that actions are taken. So even though the instruction load flag went low, the instruction register itself had not been loaded yet. We have to give it a clock signal, and that happens when we move from one state to the next. And in this case, we went from ready to fetch in this case. So that's exactly what we expect. Now at this point, we're in the normal cycle. So if I keep hitting the clock, we're now loading another instruction. The load signal went low, and there's the next instruction. And you can see that it went high again. And if I do it again, it's gone low, and one more. Now we've hit the last instruction. Again, it hasn't decoded it yet. I'd have to give it one more clock. Let's do that. And you can see that that final clock pushed us into the halt state. And that's exactly what we're seeing in our program. Excellent. We've successfully executed our second program. Now the fun starts to happen. We're going to output a value from a register out to the output register, and we should see the white LEDs start activating. So now the fun begins. We can finally run a Hello World program. And here it is. Excellent. We're going to start off by wasting a little bit of time, then load register 1, and then output it and halt. That's it. It's a very simple program. You know what to do. We need to come over here to ROM memory. Well, go back here, get the name of our program that we want to run. Put it right here. Save that. Come back to our terminal. Switch over here. Do a make all. And remember to watch the lights over here on the display. And we're doing a make all. It's loading it up. And it's loaded. So come back over here and switch back over to the program. We should see the NoOp instruction come up first. So we'll give it a clock. You'll see that the instruction load flag goes low. Yep. Goes high. We'll see our ready flag. That was the reset sequence, remember? So now we'll go give it another clock. The instruction goes low, and this time we're loading in a real instruction versus an address. So there it is, 001, our NoOp instruction. We'll click the clock one more time. The instruction goes, load flag goes low again, goes high, and there's our new instruction, 1001. That's the load register instruction. Give it another 2 clocks, and there's our next instruction, 1010. That's our output register flag. At this point, we're going to see the value A0, A5 pop out on the output register, which is the white LEDs. So let's give it another clock. Ta-da! Look at that. We get our A5, which is 10100101. That's A5. I picked that pattern just so that it looked very familiar to us. Excellent. And then, of course, a couple more clocks, and the programs come to a halt. Yay! This is our first Hello World program. We can actually see that we stored something in a register file and turned right around and moved it out to our output register, and we can see it with our very own eyes. Excellent. Now that we did the ubiquitous Hello program, we can begin testing some of the more advanced instructions. We'll start with the jump instruction first. And here we are. This is the program we'll execute. It's not that complicated. We'll load R1 with a value, the number 6. We'll output. We'll jump to this address. We'll load R2 with a 9, and we'll output that. So the program should show us a 6 on the white LEDs and then a 9 on the white LEDs. We also should see that it goes through this instruction, this one, skips over our 2 NoOps and halt, and goes straight to the load, the output, and then a halt. So let's go ahead and update our memory module to hold and access that ROM content. Save that out. Come back over here, run our make all program right there. Loads it up into the CPU. There it goes. Come back over here to our monitor program. We're going to just do a quick reset. Then we'll come back to our program. We're not going to watch the signals this much. You can pay attention to them, and I'll highlight them as they go along. But we're going to focus on the program itself. So as usual, we need to get past the reset sequence, so we'll give that some time. And it's now the ready flag went high. So we're ready for our first instruction. So we'll clock that. There it is, 1001. Excellent, we're right there. We'll give it another 2 clocks for the next instruction. So we should see 6 pop out on the white LED. So we'll give that one more, and there it is. There's 6. 4 plus 2 is 6. We'll now go to the next instruction, which is the jump instructions. We'll give it 2 more flags there, or 1 more in this case, because the output load was the second clock. And there it is, sure enough, 0, 1, 1, 1. That's our jump instruction. Now what we should see is it should jump to this instruction right down here. Now it requires an extra clock cycle, so we'll give it that one. Give it the 1, 2, and then the load instruction. See, that was 3 clocks. Excellent. It went right down to the 1001. It's not saying 001. That would be bad. It went to the load instruction. Excellent. So we'll give it 2 more clocks there. And there we are loading, getting ready to output again the register 2. So if I give it 1 more clock, sure enough, it changed to 9. 8 plus 1. Excellent. Things are going exactly as the program is intended. So we'll give it, the next instruction is the halt, and 1 more, the halt flag went high. Excellent. We successfully synthesized the jump instruction. Next is the jump and link instruction. As before, we modify the memory module with the correct program. So I'll copy this, go over to our memory program, paste it in, back over here to the terminal, do a make all. And there it goes, it's programming, and now it's uploading. And it's done. Come over here, we're ready to go. We'll do a quick reset, come back over to our program, and this is the program that we should be running on our processor. We should see it load register 1 with an A, 2 with 55. We should do a jump and store this return address. So we should jump to here, run these instructions, return, and come back. So the order in which we see the output of the registers is we should see R2 first and then R1 second. So we should see 55 and then an A. So let's give that a try. We'll run the program here. We'll get past the reset, give it some clocks. There we are. We're past the reset. I'm going to load the first instruction. There it is. Load R1 with an A. 2 more instructions. We saw the second one, R2. The code didn't change because they're both identical. And now we're on the jump and link, which is 1100, and that's what we see. So we'll give it another set of instructions, and now we're at 1010, which is correct. But the question is it outputting R1 or R2? And that's what we're going to see here in a second. So we'll clock it, and let's see what we see. And there you go. We see 5, 5. That's exactly what it's supposed to do. It has successfully jumped down to here and executed the output. We should also see a NoOp as well. So let's clock it some more, and there it is. There's the NoOp. Now here's the second half of the jump and link, the return statement. So we definitely should see the return statement show up. So let's clock it some more. There it is. There's the return statement. Now if the return statement works correctly, it should jump back up to address 3 and go to this instruction. So let's clock it 1 more. We need 3 clocks to get it to go because the return takes more instruction cycles, or more clock cycles. And sure enough, we do see the 1010, and it should output 0A. So let's give it another clock cycle, and sure enough, there is the 0A. Excellent. And we should hit the halt instruction finally. Perfect. This jump and link worked exactly as planned inside the FPGA. Nice. Let's keep moving right along and execute the shift right instruction. Here is our program. It loads R1, outputs, loads R2 with how many places we're going to shift. And R1 was loaded with the pattern. We're going to shift right 3, so that should put the bit right here. Then we'll perform the shift and then output the results in halt. So let's upload that. I've changed the content of memory already. I've already uploaded it to the processor. And now we'll go past the reset. So here we go. There's reset. Pulled in our instruction. We're outputting it. There is the bit pattern right there that we're looking for. We'll step through the next one and output the shift. We're going to shift 3 places. That's what we expect. And now we're going to perform the shift. And then finally, there's the output. And that's exactly what we expect. We moved this bit 3 places to the right, which put it there. And then finally, we'll close out the program by halting it. Excellent. Perfect. Next is the add instruction. And in this case, we're going to add 2 plus 5 should give us 7. This is the program we're going to execute right here. So again, I'll grab the ROM name, paste it here, save it, come over here, do a make all, which will build it all and upload it to the FPGA. There it goes. Come back over here and we'll look for this instruction to execute. So come over here, do a reset, and then get past the reset. There it is, ready. Now we'll do our first instruction. It'll load it with a 2 and output it. There it is. We'll then load 5 into R2 and output it. There it is. And then we'll add them. There's the new add instruction, 0010. Excellent. It's now added them and stored it into R3. Well, now there's the output of R3 and there's the results. Excellent. That's 7. And of course we halt. Perfect. The add instruction is working as well. Add sibling instruction, the subtract, is next. And here is the program. We're going to subtract 2 from 4, which should give us 2. We'll load R1 with 2, R2 with 4. We'll subtract R1 from R2 and store it in R3 and output the results. We should see a 2. Let's go ahead, grab the program name, place it in our field there, come back here, over here, and upload the new program. There it goes, and it's ready. Come over here, doing a reset. And now we'll step until the ready flag is set. Excellent. We'll do our first instruction, and it'll output it. There's 2. We'll load the R2 with 4. Should output 4. There it is. We'll perform the subtract. There it is, 0011. That's the subtract instruction. We'll then output that. There it is. 2 is the answer. Excellent. And then finally we halt. The subtract instruction is working. Nice. We're now at the branch instruction. This really expands our programming ability. So here it is. I've made this little assembly program. Again, we're loading in R1 with a 2, R2 with a 5, so that we can add them together and put them in R3. But the trick here is that we want to add 2 numbers that is not 0. So we want to branch when not equal. And so it should jump down to the LDI instruction here and load R2 with a 4, output and halt. So the output register, if the program flows correctly, should show the number 4. So let's, as usual, we grab the program, place it in the module, upload it to the FPGA. There it goes. And now we're ready to execute. As you follow along, you'll see that I'm starting it up. We're ready. The CPU is ready now. We'll execute our first instruction and then output. There's the 2. There's the 5 out of R2. There's the add, and we've just added it. We output it. As expected, it's 7. And now here's where the branch instruction, there it is, 0110. That's the branch instruction. So it should jump down to the load R2 and not a NoOp instruction. So let's see if it does that. Excellent. It went to the load R2 instruction. It'll output a 4. Perfect. And finally it halts. Excellent. The branch on not equal executed correctly. Remember, the branch on not equal is looking at the 0 flag, and 7 is not 0, so the Z flag was not set. The program acted as expected. Perfect. If we combine the branch instruction and the compare instruction, we can perform more complex programs such as counting. Here I have a program called CountUp. It loads R1 with the counter value of 0. We're going to add 2 on each round, and we're going to count up to 6. We'll add, we'll output the results, compare, and if the Z flag is not set, we'll loop. And that's how this works. So we'll go round and around until we have reached the number 6. So I've already loaded it into memory, and now I will do a make all. We'll save it. There we go. It's uploaded. Come over here to reset. We'll step until we get to the ready flag. There we are. So we'll get to our first load, our second load, and the third load, then the add instruction, and then we'll finally output it. There it is, there's the 2. So 0 plus 2 is 2. We'll then output, do our comparison. There's the compare. Do a branch, and it should take us back to the add. There we are. We're back at the add. We'll output the results right there. There's 4. Excellent. And we'll come back. We'll test a branch. We'll branch back up to the top. There's the add. We'll output the results right there. And there is 6. Excellent. And then we'll test again. We'll fail to branch. And now we're at the halt instruction as expected. And there it went. There went the halt flag. Excellent. We're actually counting up by 2 in this case, but it's working. Nice. And of course we can count down as well. So I've already loaded it into ROM. I'm ready to compile and upload it to the FPGA. There it goes. And there it is. Come over here and start clocking. And there's the ready. We're loading R1, R2, subtracting. We're going to output the results as expected. Yep. We're going to continue to subtract and go around in circles. We're counting down. There's 3. We're counting in steps of 1. There's 4, 1, and 0. Excellent. And we halted. We counted down from 5 to 0 and then stopped. So sweet. We're also counting down. Let's try something a bit more complex and use a subroutine to count to 3. Here I'm loading the address of the subroutine in R1. Here's our counter, how far we're going to count up to, and how we will count up by. We're going to count by 1 each time. We'll jump to our subroutine, which again is held by R1. So it should jump down to here. There's our subroutine. Do an add, then some sort of NoOp, and then return. And it'll return back to this instruction right here. So it'll output the results of the add. We'll compare, and if we haven't hit 3, we'll come back up here, do a jump to our subroutine, run this routine, return back up to here, and we'll keep doing this until we eventually fall out of this loop and into our halt. So let's give that a try. I've already loaded it up onto the FPGA. So again, we'll get to the ready state. There we are. We'll execute 4 load statements. There they are. There's the load. Now we're hitting the jump link. This is where we'll jump to the subroutine, which has an add instruction in it. So we should see the add. There it is. 0, 0, 1, 0. That's the add. We'll then see a NoOp. There it is. And then we'll see our return. There it is. And we'll return up to the output register 2 instruction. So let's make sure that happens. There it is. We're doing our compare. Then our branch back up to the jump link, which then goes all the way back down to the add right there. And then the NoOp, and then the return. We'll do that again. And as you can see on the right, the white LEDs, they're counting up. That's exactly what we expect. So we'll do that again. We should get to 3. We're down at the bottom. We'll output the results. And there it is. There's the output. And then we fall down into the instruction and we halt. Excellent. The program's doing exactly as we expect. Perfect. Okay, we're ready for the grand finale, the Cylon program. This is what we've worked so hard to get to. Let's give it a shot. Here it is. It's fairly large and it never ends. This thing will go back and forth with an LED on the white LEDs back and forth, just like a Cylon from Battlestar Galactica. So here we go. Let's take a look at the program. We load in our pattern, our starting pattern. We're going to shift by 1. We're going to shift left. This is our limit. This is what we compare against. When we hit this value, we switch over to a different loop. And R4 has the other limit for the other pattern. And then 6 has our jump address for where we're going to jump to every time we want to repeat, which is up here at address 6. So there's the 6 and there's the address for 6. So let's give this a shot. We know that the program's never going to hit this instruction, so the program is never going to stop. And that's what we hope to do. So I've already loaded it into the FPGA. Let's give it a try. We'll just step through a few times and see what happens. So here we are at the ready. There it is. And now we're loading in all of those registers. It takes a while. We output the first one. We're lumping, and you can see how it's going through each one. You see the white LED? It's going to the left. There you go. And there. And there it is. It's working. Now the other half is when it bounces back in the other direction. There it goes. So let me go ahead and hit the C key, and let's see how this thing runs. Now I've set the microcontroller to a very low frequency so that we can actually watch this thing bounce back and forth. So here we go. Ta-da! We have a CPU that is running its own program and manipulating the output so that we can see what's happening. You can see how it's burning through the instructions one after the other, unending. It will not stop doing this until I hit the reset button. So here I'll hit the reset, and there it goes. It started off. I'll turn the clock off, hit the reset, and you can see it's sitting there. And now I'll start the clock again, and there it goes. We have done it. We have built a fully functional CPU. Excellent. We did it. We successfully built a softcore processor, the A09. I hope you had as much fun as I did, and hopefully you'll learn something along the way. But the A09 isn't technically finished. One could always add more features by expanding it almost indefinitely, assuming there was resources available. In the upcoming final episode, all the source code and resources will be placed on GitHub for those interested in playing around and even extending it. We'll then wrap things up by reviewing all of the things that we've done and talk about what the future looks like. So until next time,